Today we're going to talk about the inverses of trigonometric functions. We have already looked at the graphs of trigonometric functions, so we have a pretty good sense for what those look like, their periodic nature and so on. And now we need to find their inverses. You'll notice on your calculator that combined with the trigonometric functions on those three buttons, sine, cosine, and tangent, there's also that sine to the -1, cosine to the -1, and tangent to the -1. That idea of raising it to the -1 power is not just move it down to the reciprocal, down to the denominator and make it positive. It's not a negative exponent. It's just a notation to denote taking the inverse of those functions. But again, you see those on your calculator, and so you're pretty aware that those exist. And now we need to find out if there are any limitations on those and how we can actually use those to understand what's going on. We've used them a little bit in the past when we were solving a right triangle and we had the three sides. If we wanted to find one of the angles, we might take the inverse sine of the opposite over the hypotenuse to get the angle. And now we'll look at those a little more closely. But before we do that, I want to go back to algebra just a little bit. Here on the screen, you can see I've got Desmos up. It's a wonderful online calculator and graphing tool, and we've used it already in the past to look at the graphs of the trigonometric functions. But now let's go back and talk a little about algebra. You can see here we have a parabola. It opens up. We've got the equation on the left side of the screen that y equals x squared minus 2. That's the graph of that particular function. We know it's a function because it passes the vertical line test, meaning any vertical line drawn through the graph of this particular equation will only cross the graph at one point. You cannot cross the graph in 2 points, drawing a vertical line. Being a function, we know certain things about it that way. One of the things we did in algebra was to find the inverse of this function. And so we may just swap the x and y values. So now we have x equals y squared minus 2. You can see that would be the inverse. It reflects about that y equals x line. And so we know that to be true. That helps prove that it's an inverse there. I'd rather have a green line. Don't know why, it just feels like a green line would look better. But there we go. We've got a function, that parabola that opens up, and it's inverse. But one of the problems we ran into is this inverse is not a function. We can draw an infinite number of vertical lines through this particular equation, this graph, and it would cross at more than one point. For example, if I were to draw the line x equals 2.3, you can see it crosses the graph at 2 points. There is one point where it only crosses at 1. That's x equals -2, crosses at that vertex of the parabola. And then we have quite a few that don't cross at all. And so we've got a number of lines that don't cross. We've got one that crosses at 1, but if you can ever draw a line that crosses at more than 1 point, it's not a function. But again, we kind of like the idea of having some functions. It adds certain characteristics to it that we could count on, like they were continuous. Oh, it didn't even have to be continuous if it was just a function. But we knew that that vertical line test would work for us. And we also knew that every x had one and only one y, which is essentially what the vertical line test tells us. So one of the things we would do when we had a graph like this parabola that opens up is we would limit the domain. And if you do that, say x is greater than or equal to 0, now we've restricted the domain to only a portion of the graph. And so one of the things we could do is not just swap x and y, but then we would solve for y. And in this case, we would add 2 to both sides and then take the square root of both sides. So we would have y equals the square root of x plus 2. And now you can see, once again, we have that inverse situation where it reflects about the y equals x line. And now the inverse is indeed a function. To check whether or not a function would have an inverse that was also a function, we used the horizontal line test. If you could draw any horizontal line and have it cross your function at only one place, then we knew its inverse would also be a function. And so we had a number of things that we could do in algebra to determine whether we had a function whose inverse would also be a function. And that becomes important when we're looking at our trigonometric functions. Before we jump into that, let's take a quick look at this inverse function that we've got, and we'll look at some features involved with that. We have, for example, our original function, and let's look at, say, its domain and its range. There were some factors or some ideas that we looked at regarding these when it came to a function and its inverse. The domain of this function with the restricted domain is now, well, x is greater than 0. So we're going from 0, and it was greater than or equal all the way to infinity. So that's the domain of this half a parabola opening up. The range on this particular one goes from -2 to infinity. And I specifically moved it away from the origin so that we could see something kind of cool that goes along with this. Let's see if I can get that color just the way I want it. And now we'll look at the domain and range of our inverse function. The domain of the inverse function now starts at -2 and goes to infinity. And the range goes from 0 to infinity. And note that the domain of a function equals the range of that function's inverse. We also note that the range of the function equals the domain of its inverse. And that becomes really important for us, especially when we're looking at these trigonometric functions. So I wanted you to keep that in mind as we move forward, because now we need to look at the trig functions, potentially restrict their domain so that we can find their inverses. And we needed to see that the domain of a function equals the range of its inverse, and so on. And that works when they are both functions, meaning the function itself was a 1-to-1, so its inverse was also a function. So let's take a look at some of our trig functions. I'll just drop these out. Let's take a look at sine. There's our sine function. We can clearly see that it is a function. It passes the vertical line test. I said just x equals a, and wanted to have a slider on there, but maybe I can't. In any event, I wanted to slide it around, but I can just do like I did before. So 2, 5, -2, no matter where I draw this, I'm going to get a vertical line that passes only one point. We also can see, however, that it is not a 1-to-1 function. If I draw a vertical or a horizontal line at y equals negative or 0.5, it will cross my function at multiple locations. So it's not a one-to-one function. That means its inverse would not be a function. If I were to graph its inverse, say x equals cosine or sine of y, you can see that that's not a function. It does reflect about the y equals x line, but it's not quite what we want to see. And it doesn't match what we're looking at on our calculator anyway, that y equals sine to the -1. So let's look at how we might restrict this domain. We want to capture all of the range values, but restrict the domain to just a portion of that. And it looks like if I were to restrict the domain from this point at a -π/2 up to this point at a +π/2, then I would capture the whole extent of the range, and I would get to a point where I'm just about to start duplicating y values. So let's make that domain limitation on here. We will do grab pi, and I actually need to make that a negative. And we will say less than or equal to x, less than or equal to π/2. So there we've restricted our domain. Oh, I didn't want to do that. Let's put our full function up there and we'll kind of hide it in the background if I can. Didn't do that quite. Let's see. I want this one to show up on top. Should, there we go. Now we can kind of see the green one on top. We've restricted our domain. And so now when we look at our inverse function, we can see that it is a reflection about y equals x of the sine function, but it has been restricted. And now we see that the same is true for this function in its domain as the last function in its domain. So here I've brought in the sine, cosine, and tangent. See, those are large enough, but let's move this just a bit. All right, and we can see that for our function, the domain, we restricted it from -π/2 to π/2. And when I did it in Desmos, I did or equal, which we really should. So that's why I put the brackets here. The range of the function goes from -1 to +1. And when I look at the inverse function, which actually is kind of a purple, bluish purple, the domain would be -1 to 1, and the range would be -π/2 π/2. And we would see something similar for cosine, except we had to limit that one from 0 to pi. So that we grabbed again from -1 to 1 on the range so that we could get the entire range within the domain. So now we know the domain and range of sine and the inverse of sine, which sometimes we call arcsine. And that's what I will usually call it. So if you hear me say arcsine, I mean the inverse of sine. And a couple of things that we really need to note here is that the input to sine, cosine, and tangent is an angle. I guess I'm kind of using computer science terms with input and output. I'm going to use sine here as an example. Cosine, tangent, cosecant, and so on. Those are all the same. The input is an angle. We would take the sine of an angle, and the output it gives us is a ratio of sides. But notice, because these crisscross here, the output, which was our range from sine, is -1 to 1. That is a ratio of sides. So that becomes the input to the arc function, or the inverse function. So arc sine's input is a ratio of sides, and its output is the angle. So I might say the arc sine of √2/2, which is a ratio of sides, and I'm asking, what is the angle whose sine is √2/2, and the answer would be 45 degrees, or pi/4. So we can see here that the input is a ratio of sides, and the output is an angle. So we will use those arc functions above those buttons on our calculators to get the angle whose ratio of sides is whatever we input. Whereas if we're using sine, maybe I wanted the sine of 45 degrees, that would give me a result of √2/2. So you can see the input here is an angle, and the output is the ratio of sides. Keep that in mind. If I ask for the arc sine of √2/2, I don't want to see anything but an angle as an answer. If I ask for the sine of 45 degrees, I don't want to see anything other than a ratio of sides as the answer. And you should feel the same way. Let's look again at cosine here. Cosine's domain, we had to restrict from 0 to pi, and its range, again, was -1 to 1, which means the arc function had a domain of -1 to 1 and a range that was 0 to pi. For tangent, the domain we restricted just like we did with sine to -pi/2 to pi/2. And the range now becomes, well, we can see this will keep going forever, right? So -∞ to infinity. And the domain of the arctangent would be, oh, that shouldn't have been brackets, that should have been parentheses. You knew better. I knew better. I ignored it. The range would be -pi/2 to pi/2. And those were actually parentheses. And let me tell you why. Remember that with tangent, we had a vertical asymptote at -pi/2 and pi/2. Those can't be brackets. Those are asymptotes. That gives us a pretty good sense for those angles. Now you can look at page 525 in the text if you'd like some more information along those lines. It gives you a table with all of the functions and their sign, their domains and ranges. So what does that mean for us? Well, let's go back to our unit circle just a bit. We restricted sine from -pi/2 to pi/2. So in this range here, we'll see results for arcsine. So the inverse of sine will give an output in the first and fourth quadrants. Cosine, we had to limit from 0 to pi. So the output from arc cosine will be in the first and second quadrants. And we had to limit tangent, we had to restrict its domain just like we did for sine from negative pi halves to pi halves. So arctangent's output will be in the first and fourth quadrants. Notice none of these show up down here in the third quadrant. So if your angle is a third quadrant angle and you try to use one of these arc functions, you will not get the answer you want. It's been limited. It's limited so that we could get a one-to-one function on our graph, and then our inverse would also be a function. So we have those limitations in place for a reason, but they do exist. So if I were looking for an angle whose sine is negative root 2 over 2, or even positive root 2 over 2, it would only give me a first quadrant answer. When I typed in arcsine of root 2 over 2 in my calculator, it would only give me a first quadrant angle. And what if I know my answer's in the second quadrant? Well, now I have to say, well, while this gives me 45 degrees, I have to remember that arcsine only works in the first and fourth quadrants. And so if it is a second quadrant angle, I know that the reference angle is 45 degrees. So the actual angle is 135 degrees. So sometimes the answer we get will be a reference angle and not the actual angle that we want. And that's all due to those limitations of ensuring that we have a one-to-one function and our inverse would then be a function. So those are limitations in your calculator, meaning the answer your calculator gives you, though correct, might not be the answer you're looking for. It may actually be a reference angle. So be prepared for that and watch out for it. Let's take a look at some of the types of problems we might see in this section. We might see, for example, the arcsine of root 2 over 2. The angle whose sine is root 2 over 2. And we've already answered that one as 45 degrees or pi over 4. What if we've got the arc cosine of negative 1/2? So where is the cosine equal to negative 1/2? Well, if I draw my unit skittle here, cosine are the x values, so negative 1/2. I can draw a vertical line there, and I can see it crosses my unit circle at 2 places. So I've got a couple of angles here. Remember, arc cosine works in the first and second quadrants. So if I plug that into my calculator, I will get this second quadrant answer. Or I can say, well, 1/2, that looks awful familiar. My 30, 60, 90 right triangle, which we used to create our unit circle, had the ratio of sides 1, 2, root 3. And there's the 1/2. Cosine is adjacent over hypotenuse. That would be 60 degrees. So my reference angle here is 60 degrees. That means the actual angle is 120 degrees. Now, if I want that third quadrant angle, I'll have to recognize that this becomes a reference angle of 60 degrees, and I'm adding 60 to the 180, which would be 240 degrees. Now, if I wanted radians, 120 degrees would be 2 pi over 3. And this would be 4 pi over 3 radians. So those would all work. Now, as it turns out, because we're not limited to once around the circle, I have to consider every coterminal angle with this. So I'll take that 120 and I'll add 360. And I'll add another 360 and another 360. So it's like 360 times any multiple. And the 240 plus 360 times any multiple thereof. So that gives me all of the angles in existence whose cosine is -1/2. So sometimes we have to look at all of those times that those occur. Other times we just have to look at within a certain region. And it'll say from 0 to 2 pi, for example. If it says that, then it's looking for a radian answer and only within one revolution around the unit circle. Again, we can plug that into our calculator, the arc cosine of -1/2. I have my calculator here. And when I plug that in, it gives me 120. That's all it gives me. It won't give me that third quadrant angle. It won't give me every coterminal angle. And so I have to use my understanding of inverse functions to carry it beyond what my calculator says so that I get the full answer. What if we were given the arc cotangent of 0? Now that looks rather weird, doesn't it? We don't even have cotangent on our calculators. So cotangent is restricted, just like tangent, from 0 to pi. So where within that range of 0 to pi is the cotangent equal to 0? Let's grab another color here so we can use this unit skittle I drew. We're looking in that region. Now let me get a better color here. In that region, where is tangent equal to, or cotangent equal to 0? Remember, cotangent is cosine over sine. So sine can't be 0, but cosine could be 0. Cosine would be 0 at the y-axis. So it looks like pi halves, or 90 degrees, would be our answer. It's the only number within that restricted range, the cotangent of 0. What a deal, huh? All right, now, one of the things that we did while looking at inverse functions, and this harkens back to algebra again, is recall that we're comparing f of x and the inverse of f of x. We found that, recall the composition of functions, the composition of f and the inverse of f of x just gave us x. You might have seen it written as this: f of the inverse of f of x. That always gave us x. Turns out that that works pretty well for these trigonometric functions. The sine of the arc sine of x does equal x, but only when x is in domain of the inverse function. So if x is in the domain of the arc sine, then the sine of the arc sine of x equals x. Same for cosine and tangent. We had the cosine of the arc cosine of x, that would equal x, or x in the domain of the arc cosine. So let's see a problem that deals with this so that you can see what we're talking about. If we took the cosine of the arc cosine of root 3 over 2, is that root 3 over 2? And it looks like it ought to be, right? So let's see, the arc cosine of root 3 over 2. I know root 3 and 2 from my 30, 60, 90. So root 3 over 2, the arc cosine, the angle whose cosine is root 3 over 2 is 30 degrees. And so now, essentially what I'm finding is the cosine of 30 degrees. And the cosine of 30 degrees is indeed root 3 over 2. Notice how I did that. I worked inside the parentheses, almost like we're looking at PEMDAS here, and I evaluated that arc cosine first, and then I evaluated the outside function of cosine of 30. And why would I do that? Well, sometimes x is not in the domain of the arc sine. And let's see if we can find an example of that. Maybe the arc sine of the sine of 3 pi over 4. Once again, we've got a function and its inverse, and we're taking the composition thereof. Well, what's the sine of 3 pi over 4? 3 pi over 4 is over here in the second quadrant. That's 3 pi over 4. And the sine thereof is, those are the y values. That would be root 2 over 2. So now I'm looking at the arc sine of root 2 over 2, which is pi over 4. Because 3 pi over 4 is outside the range of arc sine, my result will not be x, it will be something else. And so I always evaluate these in 2 steps. I evaluate the middle, the inner function first, and then the outer function. Often it's so quick and easy, you don't even have to worry about, oh, does that really equal x or not? Because evaluating the inner function happens pretty quickly. If we saw the arctangent of the tangent of pi over 6, pi over 6 would be the 1, 2 root 3. The tangent of pi over 6 is 1 over root 3. I won't even rationalize it right now. It's okay because it's an intermediate step. So now I need the arctangent, the angle whose tangent is 1 over root 3. And the angle who has that tangent would be pi over 6. So here, in this case, we did end up with the same x value. But I made it a 2-step process just to be sure that it truly is x. Pi over 6 is within the range of arctangent, so that works well. Again, 3 pi over 4 is not within the range of arc sine, so that one didn't carry forward. Now let's see some other options here that are perhaps a little different, so we might not quite expect what we're getting. Let's try the sine of the arctangent of -1. Well, let's evaluate that inside the brackets. Where is tangent -1? Well, I know tangent of 45 degrees is 1. But this is -1. So looking at our coordinate system where all students throw chalk, where is tangent negative in the in the second and fourth quadrants? Arctangent, if you'll recall, only works in the first and fourth. And so I'm really looking down here in the fourth quadrant. The arctangent of -1 would be right there in the fourth quadrant, 45 degrees shy of 360. So that would be 315. And so now I need the sine of 315 degrees. And the sine of 315 degrees would be negative √2/2. That would be the sine of 315. The reference angle would be 45 degrees. We know that the sine of 45 degrees is √2/2. We're in the fourth quadrant, so it would be negative, and that would be our result. All right. Let's look at another one that's kind of odd. What is the sine of the cotangent, say arc cotangent of x/2? That looks really weird, doesn't it? Cotangent. Now, arc cotangent is only defined just like tangent in the first and fourth quadrants. Here it's positive, so that would be a first quadrant angle. So let's take a look at our first quadrant here. We've got some angle up here. The cotangent is x/2. So that's adjacent over opposite. So now I have those sides labeled. Now I need the hypotenuse. So recall that a² + b² = c². If a is x, b is 2, then c would be the square root of x² + 4. So why did we need that? Well, we're going to take the sine of this angle. All right, so now we know, we'll call the angle theta. So the angle whose cotangent is x/2 is theta in this example. And the sine of theta, again, going back to our figure here, sine is opposite over hypotenuse. So 2 over the square root of x² + 4. And I think they'll let you leave it with that radical in the denominator. If not, then that becomes 2 √x² + 4 over x² + 4. Just rationalizing like we have everywhere else. Really, I think the software will allow you to enter in 2 over x² + 4 to make that work. So that is the introduction to the inverse trigonometric functions. We had some limitations on domain and range that we had to put into place so that we could get one-to-one functions, and therefore we could find their inverse functions, which are on our calculators. We now have those limitations. The arcsine and arctangent show up in the first and fourth quadrants, and the arc cosine shows up in the first and second quadrants. So remember that when using your calculator, that the answer you get will be in one of those quadrants. It won't necessarily be in the quadrant you're looking for. So if you get an answer, or if you're asked to find the arcsine of an angle who's down in the third quadrant, What you get from the calculator will be a reference angle, and you'll have to add that to 180 degrees or pi to get the actual answer you're looking for. So beware when using those arc functions on your calculator. But if you have questions, let me know.